Hello everyone and welcome to today's talk at the Bangalore Theory Seminar Series. Today's speaker is Mrinalkanti Ghosh. He is finishing up his PhD at the Toyota Technological Institute of Chicago under Professor Madhu Tulsiani. Prior to that, he completed his master's at IIT Kanpur and is currently a senior research fellow at IISc with Professor Lewis. And today's talk is on approximability of matrix P2 norms. Welcome.
Thanks for that short and sweet introduction. I'm going to talk about this approximability of matrix P2 norms. This was jointly done with Vijay Vatripalus. He was a student at CMU, now is at Waterloo, joining as faculty. Venkat Guruswamy is a faculty at CMU. Uyum was a student of Venkat at that point. He was a postdoc at NYU, now he's a faculty at UH. And Madhu is my advisor. Those are the people involved in this work. A little bit of bookkeeping before we get into the thing. As you can see, there are only 13 slides, so I want this talk to be super interactive. So stop and ask me questions. If something is confusing, if something is not clear, or if you just want to break my flow and sort of ask me to pause. That's okay. So the purpose of this talk is to introduce you guys or reintroduce you guys to this matrix P2 norms and connect it to some other problems in TCS, and toward the later half we'll talk about what we did for this problem. So P2 norm for a linear operator A or a matrix A is just this number. It's the Q norm of AX normalized by the X norm, the P norm of X. And of course, this only makes sense when X is not equal to 0, and for completeness, P norm is this. Note that we will not be working with 0 norm because that's not 1. So for us, P and Q, everything is bigger than 1, but it infinity is 1. So that's the problem. Now, notice that the this thing is linear in X, this entire thing, because A is linear and then the Q norm is linear. So you can normalize this further to say, well, restrict yourself to the case where P norm is actually equal to 1. And then you can replace this soup by max because it's a convex set. So this thing is achieved. Now, what is it saying? It's saying stretch of A under different norms. Sorry. I'm just using closed boundedness. It's a continuous function, so it takes the maximum. Yeah, you said convex. No, I said compact. Compact. Oh, maybe I misspoke. But what I'm using is compact. Yeah. Okay. So what is it? Was it measuring? It's measuring stretch in some sense. Let's see. Let's assume that I have the phi. Okay, it is actually the it. And let's take the map with just scales for y by some half. Half. And then you are asking, well, what's the L1 diameter of this ball? So that would be the L5 to L1 of this operator. So L5 to L1. So if you can bound, so this is the direction that clearly maximizes the direction. So that's the solution to this X, and that's the stretch. And if you are doing it for 2 to 2, then it's like the singular value. So that is fairly general. But it generalizes many more problems in this. So analytic sparsity can be seen as trying to minimize this number. So if you have a sparse vector analytically, so if few entries are big, other numbers are small, then you can sort of see that if you are taking the 100th norm, then like the large entries sort of pick up. So the contribution to the large entries is what we're looking for. And that's a very good approximation to analytic sparsity. And this has been used for decimal learning, sparse recovery, problems like that. In this case, I'm only going to talk about problems of P to Q where P is 2 and Q is bigger than 2. These are the special type of problems that we're talking about in this slide. So the next problem is 2 to 4. And from what I understand, this is related to quantum information theory. I have heard it mentioned, but I don't know much about it.
Thinking of x100 by x, like the 100 now by 2 now, how does it become, you know?
So if you have like a look at all possible.
You're going from P to Q, P is the setting is 2.
Right.
So you're not.
So take the unit sphere. So as you can say, like this is the solution. You can always think of x as norm 1. So think of the unit sphere, and then you're trying to ask for what's the sparsest vector in some sense, because if you can sort of concentrate all your mass on one coordinate, and that shows up in the 100 because the contribution is like a to the 100 for that number.
What is A?
A is the identity map. Here A is the identity map, but you could look at a projection map which will ask for planted like a sparsest vector in a subspace, and that's exactly the kind of problem these type of things do. So if you're a subspace, so there the A is the projection map, and you're asking to find the sparsest vector in that subspace.
So the sparsity, like the extreme case is 2 to infinity. We're saying among
yes,
unit
exactly. So 2 to infinity would be great, but infinity norm as you no, it's not like that. Yeah. Like you don't have access to this type of expressions. You can't like use convex relaxations in some sense. No. Yeah, logging would be a great idea. Yes, yeah, you can stop at logging. In fact, these algorithms that I was mentioning, this is by Goddard and Snyder, and they use some of squares techniques which are convex. They in fact use 2 to 4, not even 200, to do this. And 2 to Q for even Q is so known to be equivalent to finding P if in a graph all small sets expand or not. So this is known as a small set expansion convector, and this is in fact equivalent to small set expansion. Q is some even integer which is bigger than Q. So mention. So Q shows up in the relation between the how good is an expander versus what the loss in the parameter. So it's a little intricate to get into the parameter details. So I'm not talking about it, but you can think of Q as four rules. A is the projection to the top eigenspace. So gets into G. I don't want to like.
Any idea why 2 to 4 itself like starts having?
So 2 to 2 is easy. 2 to 3 we don't want to talk about because 3 is odd. Okay. Because the absolute value comes up. So the next best thing is 2 to 4.
And that itself
starts being useful. So that's roughly what's going on. Yes. And this type of norms are called hypercontractive if Q is bigger than P. But in this case, we're only talking about when P is 2. And so let's go to the next case where next case is where P is bigger. So that's reverse hypercontractive or bigger than equal to. That's how it's made. And of course, 2 to 2, as I said, it's SVD problem, and it's easy and useful everywhere. Let's look at a different problem. This is not immediately obvious why it has anything to do with matrix PDQ problem. We'll show it in the next slide, why it is related. But this is useful in combinatorial optimization. This, in fact, came up in functional analysis. This was introduced by Grothendieck in 1953 in his famous resume. And he basically asked the question: if I try to maximize this bilinear form over real numbers, over real matrices, and these are not necessarily square matrices, over plus minus 1 variables, like what can you do? Can you actually come up with a good approximation? And he showed a constant factor approximation for this. In fact, these days you can formulate what he showed in standard STP language. You can basically say that he showed how to relax this problem using an STP and showed that the STP has a good integrity gap, boundary integrity gap. Yes. No. These are variables. Xi and yi are variables. X1 up to xn is the vector, and yi up to yn is the vector.
Is that all the expected values that xi is going to be constrained on the xi?
Yeah, that's it. Like there is no interdependence between xi yi or xi x1 x2 for that matter. Now, if you and a long line of work went into figuring out what is actually the integrity gap of this STP relaxation, which is called the Grothendieck constant. Grothendieck proved this too long. Grothendieck proved. I forgot Grothendieck's upper bound. So this Grothendieck proved this is bigger than pi over 2, and here 2.3. Reads in an unpublished manuscript in 1993 proved a better lower bound of 1.67 of magnitude. And Krivin in 77 gave an upper bound which is better than 2.3, and this is where people were stuck for a long time until this was done by Braverman, Makarchev, and Endowed, which broke this barrier by 10 to the minus 6 or something like that, but this is not the right number we know. And we also know that there is a way to approach KG from above. There is a sequence of a scheme, like there is a scheme where there is a sequence of algorithms which approach KG from above, and in the limit actually it matches. So we know that. So potentially, if you can put, so this is the level 2 of that scheme, but if you spend more time, you can potentially get better. But why do you care about KG? Yeah. What is it good for? It's good for because you can. Right. Something happened with the slides. So if you replace this plus minus 1 with 0, 1, you get the cut mark, which is asking if this was like a adjacency matrix of a graph, find S and T such that maximum edges are cut, or maximum edges go between S and T. That's the cut, and that's very useful because this can allow you to do some sort of weak regularity decomposition of your graph as shown by this. And if you have a weak regularity decomposition of your graph into cut matrices, then you can apply this to sort of design better algorithms for your combinatorial optimization problems. And Alan now basically showed how to use these Grothendieck problems approximation to get a good approximation to the cut norm and then make everything algorithm. So Chris-Curran's algorithm works for when KIs are -1 to 1, and they basically showed it to do it for every matrices, and that's the concept. Now, as I said, we'll show in the next slide that this is actually an infinity to 1 norm of K. In fact, if you look at this expression, this is bilinear. So xi squared never appears in any of the term. So you can say that you can relax this -1 to 1 to like the continuous interval, because for any so you can always go to one of the states for each xi. So fix xi, fix everything but xi and take the derivative, because there is no xi in the derivative because it's a linear term. So it's positive or negative, and you can go to one of the states. So the optimal is actually always achieved by ±1. So therefore, you can relax this ±1 to -1 to 1, and then this automatically suggests an STP relaxation. You replace xi by vector or vector normal. So that's the STP relaxation. Oh, you replace xi by a L1 norm vector ui, and yj by a L1 norm vector vj, and replace this product by a minor product. That's it. like you have a bound, you have a bounded real value, you just replace the no, replace the real number by a bound.
By this, so A is the adjacency matrix in this.
I mean, you don't. Yeah. So if you have diagonal. So don't think of it can be negative. So the thing is, the crucial bit is there is no square term there.
That's getting. I was just getting back to the fact that you're saying like.
Right. So when this is for a bipartite, so when this is a bipartite graph, then it makes sense to talk about xi and xj, which are unpaired. When you're talking about a graph, then you need to apply to the Laplace. And for if A is PSD, then you can sort of also show that the in the maximizer xi is equal to y because of eigenvectors.
But the easier way to look at it is consider bipartite.
Yes.
Xi is the eigenvector here.
Yes, and y is a eigenvector here, and then that's the cut. That's easier. But in a bipartite graph, it's a trivial problem because you would always be essentially to the both sides.
Sure.
Okay, so because then xi you cannot just go to one of the extremes because then sort of the value of xi depends on like what the derivative is, like switch at some point. But the derivative is independent of xi, so you can actually go to one of the extremes.
Like the whole is bound. People study hierarchies and for higher levels, like integrating about the change in a sharp jump or something.
We don't know. We just know we don't know rates of convergence. We just know in the limited convergence. Yeah, that work is due to the regime and doesn't know. That shows that there is a hierarchy. All right.
We can relax it irrespective of whether it's infinity to 1 or.
Yes, in fact, we do. We do. So you need to replace this by not infinity, like p1 now, things like that. That's exactly what we do. That's the exact last line. Right. So let's get back to the problem. PDQ norm. It's the maximum over this. Now, pretty much by definition of dual norms, you can write this norm by another maximization. And then use adjoint because the serial matrix is just a transpose, and then switch x and y. Then that's just q star to p star. That's exactly that. So there is a little bit of a symmetry between the p to q and q star to p star. But oh, I forgot to mention q star is the dual norm of q, which is 1 over q plus 1 over q star 1. But this doesn't change the nature of hypercontractivity versus non-hypercontractivity. If P is bigger than Q, then Q star is bigger than P star. So it doesn't change the nature of the problem. If you start with hypercontractivity, you still get hypercontractivity thing. But it's basically connecting P to Q to P star to Q star. But like if you're talking about algorithm versus hardness, like all of these are equally hard to do. So let's get back to the picture. We are looking at P to Q norm. This is the P, this is the Q, and we're including 1 and 3. Now, 2 plays an important role for some reason. I was talking to a function analyst, and when I said 2 plays an important role, he said that's expected. So apparently it's expected that 2 plays an important role in this picture. Yeah. Because we are doing dual norms. So this dual goes there. As good as because the map you're taking is the dual map. He goes to twisted. All right. And what we said, and this is the line P is equal to Q, and this is the hypercontractive. This is the reverse hypercontractive reason. And the picture should be symmetrical according to the diagonal because of that symmetry. Now, what do we know about all of these regions? In this case, when 2 is in the interval, we know a constant factor algorithm. In fact, infinity to 1 lies here. And we know this how to do this for all p's and q's as long as 2 is in the interval. There's a long line of work which establishes this. Convex relaxation, pretty much. You need to do, yeah, it's convex relaxation. We'll actually see the convex relaxation at some point. So that's the good thing we talk about our, when I talk about our result. So we actually know the constant here, depending on based on P and Q, and we know the right behavior, even though it's not right exactly. So that's part of our work. Nestrov gave it an arbitrary constant. Steinberg also gave it a constant, which sometimes are comparable to ours. Sometimes, I mean, we sometimes do better. She sometimes do better. But the hard constant doesn't depend on P and like it depends a little bit on the. Okay, let me not go into that detail. No. So this is in. So when I say constant vector approximation, you are going to do multiplicative approximation. So the matrix doesn't appear in the neither M nor N nor the matrix appears in the picture. It's for all matrices of any by M matrices.
What do you have?
Like standard for max cut when you say 0.87 applied approximation, it doesn't matter what the number of pages, what are the weights. It's like that. Right. So in this case where it's still reverse hypercontractive, but 2 is not in the picture, then Bhaskar and Vijayaraghavan they show the hardness of NP-hardness basis, assuming NP is not in d time this. They give an approximation lower bound of this. Like this number appear in both in the assumption. But this is kind of interesting, or at least when I first realized this, found it interesting, that it's a continuous problem. Like A is real, you're optimizing over real bodies, and then you get proving an NP-hardness starting from a reduction, which is discrete in nature. You start with theism for this reduction. And in this regime, we know an ETH hardness, but it's not. It's not as strong as we suspect it is. Some sort of it rules out some features, but we suspect that 2-to-4 norm is really hard, and 2-to-4 norm lies here because of this connection with Mozart expansion and quantum function theory, and we like a better hardness here, but pretty much have no idea how to do it. Okay, so we prove a new NP-hardness for this reason, and this is assuming NP is not in randomized polynomial time of this, and we can in fact determine this constant within 1 point some number 1.10 to the minus 10. This number, and we can recover this result also, but under the weaker assumption of NP not in R randomized this time, not in but it's like the same set of framework which gives all these hardness results. And when I say we determine this, we actually give an algorithm which matches up the constant of the right number. So let's get formal. Let's look at the
So it certainly has to be the case like this orange hardness. This has a dependency on at least P. Like I'm looking at this exact line that's separating P to.
Great. So that if you go like a constant above it,
yeah,
we don't have any dependency. But if you are like 2 plus 1 over log n, then we don't know how to do it.
Okay. So there has to be a band of discontinuity.
Yes. So if you go like any constant above, sure. But the dependency on that, if you allow this number to depend on n, then we don't know. In fact, that's a very good question. How to do 2 plus 1 over log n to 4? Like so, 2 plus delta to 4 is here, like in one of these regions. So yeah, so here 2 plus delta to 4 is here. We just don't know how to do even 2 plus 1 over log n to 4. And similar things happen with like all these boundaries. If you allow this to depend on n, then we don't know. But
and for the problems, let's say small set expansion, for which you need say 2 to 4.
Yeah,
it is like that delicate, you know, like you
2 is needed.
2 is
needed.
okay.
Yeah.
There's no Lipschitz gods don't help you.
No, it doesn't. Q is not that important because 4 6 all of this works, but 2 is needed. Yeah, that's very interesting.
That functional analyst goes up to something.
Yes, he in fact started an entire field of theory of spaces, and that started with that paper. Yeah. Oh, it's a NP-hardness. Listing?
Yeah,
Right.
that's NP
The time of this.
and your result is
NP not RP of this.
This is the for the
Yeah, but I mean, the time and RP is not. We're going to speak this that much. Yeah, I know. All right, so let's get to the actual numbers. So this is for the green box. 2 is in the interval, or think of infinity to 1. So we get an approximation factor for all epsilon gamma p star gamma q, where gamma p to the p is just the standard Gaussian model. Right. So this is the blue region. We are not going to talk about the mascara region too much. So this is for the blue region. You get this approximation. Yeah. So assuming it is not possible as possible in another time. So as I was saying, I can do 2 plus delta to q, but I can't do like 2 plus 1 over log n to q. That's surprising. And in an adjoining work, we basically show that you can also get an algorithm which is like 1 plus delta times this constant. So it's up to this 1 plus delta, it's right. So that's the overview of the result, and then we'll go into the result on the next slide. So it's a good time to ask questions if there are any about what we are actually doing.
The Gaussian movements remind me, how do they change if I like this term itself would not vary drastically even if you go from the
So full norm is 3, and then a high norm like this. So don't have any polling factors.
yeah. It's not okay.
It's not drastic, but there is some change.
There is, but there's some very crucial aspect of being in that regime that you get.
Oh no, that's the artifact of a proof. Like one of the things that we proved last. I mean, that's the next slide. Why 2 is needed in this regime is like an artifact of a proof. Okay, why don't we go? So we start first. Yep. You take a standard Gaussian, raise it to power, like absolute raise it to power, take the expectation.
Yeah, but what are the numbers like?
Oh, so the gamma 2 is 1, gamma 4 is 3. And then you can write this down by a double factorial. It's a closed form solution. It's like a p, gamma p to the p is like e to the p over 2. Approximately. I'm losing a lot of factors. Okay.
Delta is a fixed constant.
It's a fixed constant.
Not for any arbitrary.
Not for any arbitrary, as far as we know. There exists.
This is one-dimensional Gaussian.
Yeah, this is just one-dimensional Gaussian. Right. So this is the p to 2 when p is bigger than 2, and by the symmetry we saw before, if q is less than 2, you can get hardness of p. This extends the p&lt circuit. So they gave a hardness for the authentic problem when the matrix is PSC, because it's authentic. They as part of their proof, they needed infinity proof. We extend this, and this is actually the bulk of the paper. Our analysis is similar to their, like our gadget for the reduction that we do is very similar to theirs, but our analysis is requires some more tools to extend this infinity to p. But that's what we started. The reduction that it produces, the matrix that it produces has this nice property that, so this is the completeness case when norm is 1, and this is the soundness case when when the set is not satisfiable, then the matrix it produces has to be not go to like 1 or 2. But the nice property of the completeness case is it's a projection on the completeness vector or any polynomial. Now, given these two, you can already see where I'm going with this. You can look at A transpose. That's a norm from 2 to Q, and A is from P to 2. So if I just take the multiplication, then I can get potentially P to Q if such things hold, and it does indeed hold. So that's the argument for this case. And you get in the satisfied, and this is important because in the composition, like you don't lose anything. So A of x goes to x. So you will, in the completeness case, you still get 1, but in the soundness case, you get gamma p square gamma 2. That's this case. Now let's talk about. So this is the green case. Let's talk about the blue case a little bit.
Where did you use the pattern?
This doesn't work unless p is greater than 2. Okay. So if you're doing the composition, you need to go through 2.
The fact is because of the order if you apply C. The first apply C is the
right. No, the fact is to prove this thing, you need like this. You need. So we use Keating gather, which is basically saying if you look at like a vector. You give a vector and then you take ID random variables plus minus 1 and take the inner product of the vector and reduce it over p. How does it concentrate? Concentrate like gamma p times the norm of the vector over p, and that only works for p when it's bigger than 2.
like the typo type.
Yes, exactly. It's the typo type thing. It's exactly that for that reason. This works. It would be great if we could do like without if you could bypass to somehow it would be great, but we just don't know how to do it. Good. So let's get to the next set of ideas. So we start with the same hardness, P to 2, and then we use geometry. So here is a great result from geometry. It says, well, it's a bit more you will see a picture of this maybe. It says if you have like a random matrix, Gaussian matrix, stall, n is bigger than n, significantly bigger than n, then Q norm of GZ is roughly the Q norm of Z. Or there's a scale, like you can make it an ellipse. So let's see the picture. So let's look at a ball, which is m dimensional. And when you're looking at into the keyword to random projection, so this you can think of it as a random projection after then it looks like an ellipsoid, which is like an A2. And this requires some cool properties of these Gaussians, like the fact that this Gaussian entries are independently drawn, and there are some rotational invariants, like all of these are needed for this fact to be proved, but it's known fact high-dimensional probability. Yeah. So you need to. So the n that your target is like a So you thinking of this as this is like a projection. M is it's a tall matrix. If I misspoke, then I apologize. It's a tall matrix in the sense like the columns are like large compared to the rows. Yeah. So so if you have n, then this is like you need to go like above that. So you need to think of this as the target space. So this is your final m, and you start with n. So replace n with m. That's how small does n need to be? Depends on the Q. Like the projections dimension is this exactly this. So if you're doing it for higher norm, you need to do it for higher norm. And this is exactly why 2 plus 1 over 2 doesn't, like 2 plus 1 over 1 doesn't work. Also,
this is a generalization of Johnson-Lindenstraus type idea.
yes.
Like,
Yes, but the point is the Q norm has a lots of corners. It's not like a nicely unitary symmetric. But you can sort of, the idea is if you throw it random microscope, you will almost never get a corner. That's the point. You'll see an ellipsoid, and if it's an ellipsoid, then it will itself do. That's that. So corners are like very sparse in your space. That's an intuition. I mean, if you have a metric which is like the norm is you define the ball as ax to norm is less than or equal to 1, where a is a PSC matrix, that's an ellipsoid, and then you can easily turn it to an actual circle by saying multiply by e to the half or something like that, e to the minus half or something like that. Right. So then you get a P to 2, and then you just say, well, if I look at the Q norm of this guy, that's roughly the Q norm. So G of A, P to Q is roughly the P to 2 norm, and then we know how to do this. And that's pretty much, that gives a constant factor approximation where this constant depends on the, this gives a constant factor approximation where the constant is this. And then you can tensor this. So you can take the matrix like GA and tensor it to a large enough power. And we know that for hypercontractive norms, the tensors have a nice property that the norm actually get a product. So you get like constant to quasi-quadratic. That's and we have to stop because this is random, so you get a randomized reduction, and you have to stop at log n because if you go below above, then you get reduction is large. So if you take your T to be about log n, then you get a quasi-polynomial reduction, randomized quasi-polynomial reduction, and then you get a quasi-polynomial hardness. Exactly as promised.
No de-randomization of movement.
Not as far as I know. Not as far as I know.
JL has it.
Yeah, but this actually, I don't even know how to do it when G is not like a Gaussian. If it doesn't have a rotation symmetry, I don't know how to do it. Because this uses like this Talagan measurizing measure and all that, and that requires rotation is quite useful. Yeah, there's a very nice book on this high-dimensional probability. Yeah, exactly. That is this. Yeah, it's very nice book. All right, so let's go through what we did. We started here by reflection along this axis, you get that, and by taking a product, you get that. By embedding, you get that, and by reflection, you get that. And this, we do it by a different type of embedding due to set mapping. And it uses this p-stable distributions, and the embedding is tricky here. So that's the overview of the hardness. Let's get into algorithm when we are here. So we want to do something like infinity to 1 prevent rounding algorithm. So prevent did it for infinity to 1, and that uses hyperplanes in crucial ways, actually inspired by Gomez in some sense. For the analysis of this. And we'll talk about that after lunch in more detail. So stick around if you're interested. But the overall idea is, as we were saying, we can still write this thing as a relaxation, where this is the p norm and this is the q norm of those vectors, and turn that into a vector. So replace these guys with a vector, but you want to say the 2 norm or p is bounded, and this thing is a polynomial only when p and q start getting to 2. That's why our algorithm also knows that really is. Otherwise, it doesn't. Otherwise, this thing is not a convex relaxation, and we don't know how to solve it. But once you have a solution like ui and vj, we know how to round it. At least for this. Yeah, pretty much take a hyperplane and then do something, but you need to do a pre-processing that's inspired by Krivin. Yes, it's a nice, I mean, Krivin's rounding is very nice, and we basically follow their approach, but our analysis gets tricky pretty much after the first couple of days, because there is a signage. We will talk about it afterwards. All right, so this is all I have to say. And the questions that remains 2 to 4, as I was saying, it's a very interesting problem. It's connected to so many problems. We don't know, we want to get a good bound for this. And if you notice, the p norm when p is an integer bigger, so q norm when q is an integer bigger than 2, or even integer bigger than 2, then the q norm is actually a polynomial. So you can ask for well, if I'm on N2 ball, give me maximize the degree 4 polynomial, arbitrary degree 4 polynomial. If you're trying to think about hardness, let's not worry about 4 norm for a moment. Let's try to give a hardness for degree 4 polynomials on trying to maximize that to what it is. So can you do something interesting there? Now. So other thing is, can you do this for general operator norms? And the hardness that I was telling you about, it's like a to the t times a. So it's always going to give a PSC matrix. So the hardness is only for PSC matrices. Can you improve a better hardness for matrices which are not necessarily PSC? In fact, there is there was a paper which appeared in this IISc by Vijay, Uyung, and Madhur, which did so for infinity to 1, the gap is pi over 2, so they give pi over 2 minus 1 epsilon, but epsilon is 3 to the minus 6. But you can do something better than PSC matrices. We don't know, but there is reason to believe that you can do exactly P of G, like the constant, but we don't know how to get there. I mean, reason to believe that. Not necessary. So that's an interesting question. Can you improve the hardness for this staging when the matrix itself is not PSD, and can you do it? And that's all. More questions.
This paper, keep going back to combinatorial instantiations of it, but the special state structured matrices are better results maybe for the regimes where you don't have constant factors, like the hypercontractive regime, give you some nice properties about it.
Right. I do not know the A's part in the figure. Yeah, sure. I mean, so this is already slightly Yeah, so it is slightly general than let's say matrices, because for matrices the A we're going to apply it to will be the Laplacian, which is already placed, and you can do the reciprocal for approximating patterns. So you can already do a little bit better than what we can do. But when you have non-PhD matrices, then I think it's tricky. And I don't know if I allow some sort of special structure on non-PhD matrices, can you do that? I don't know.
Related question.
Yeah.
Problem. Remember some problem, some will be
Oh yeah. So yeah. So the question is, given a matrix, can you given a so this is for n by n regular matrix, bipartite matrix. If you are trying to figure out, this is by O'Donnell and you know, this is by Raghavendra and O'Donnell. Ryan and Prasad. So they proved that if you have like a bipartite matrix up to UTC, it's hard to approximate this thing any better than KC, whatever that KC value is. Yeah, so that's and in fact this hardness from the Dells this last hardness is sort of trying to go beyond, like they're trying to sort of follow their approach up to degree 1. So their reduction has like many degree terms. They can follow their analysis up to degree 1 term in some sense, and they can get an improvement. That's at least what articles so they do. Questions?
Like, so if assuming like m or n is small enough constant, the exponential the net arguments might work.
Net arguments might work. There is a sub-exponential time algorithm for 2 to q when q is even here. That gives like n to the 2 over q, like exponential n to the 2 over q time. This is also due to
Yeah, integral targeting for itself to the
yeah. I mean, apparently it has connections to quantum separability questions as well. Given a quantum state is separable or not, like determining that includes the sum of the two quantum cases. So it shows up in many cases.
Did you mention 3 or odd numbers will not be
Absolutely. I mean, we don't want to deal with absolute value because as soon as you're absolute value, you need to somehow like make it convex, like nice and continuous. It's smooth.
probably a tangent, but a lot of these norms are. So I'm thinking of from a perspective like Gaussian weight, where you apply it, like instead of computing it as like a max, you compute expectations over Gaussian.
Right.
But probably that you can do in
Subgaussian.
Yeah.
Using Subgaussian.
max.
This is the max, which is actually important.
On average is.
So I have to suspect.
Yeah. Sampling might be slow. Okay.
Maybe. I'm not sure.
I'm saying that do you see any other application in commutative approximation algorithm? Is it max cut or not with application?
Right. So phase convention, if you can apply regularity decomposition as a max cut, then that's a good place to start. So this paper of Luca and others, when they do local rank max, so they are actually do cardinal approximation, and they can do cardinal approximation well by not necessarily this type of techniques. to sort of run it at like even LP and down it. Yeah, so if you can do control, then like this. Oh, by the way, I forgot to mention. Control is a constant factor related to certain constant of the matrix. Like, it's between 1/4 and 1. So that's why it is.
What we could think about gauging what is the value?
I don't think we know the right numbers. Or even suspect. I don't think we so. Or at least I didn't see it mentioned. Yeah, I didn't see it. And this thing is interesting. Like this lower node, it's unpublished, but it's interesting. I don't know.
These densest graph or subgraph problems have these bilinear forms, right? But that is not connected to these.
No, because it's slightly more general than polynomial optimization. So as I was saying, 2 to 4 is like a good analog of sparsity, analytic sparsity. But for decays, you sort of need to figure out the maxima at each, like at different levels. It's not like a one polynomial that you can write. It's slightly more general. So even if you have like a good polynomial approximation algorithm, that doesn't necessarily give you the good figure of the decays. And this is like a specific suspect that this is sorry? Oh, so given a matrix, if you can figuring out the integrity curve of the SCP relaxation, so that's exactly kg after this.
This is the best possible method.
So that analysis uses like rather than this relaxation uses CSP and uses that and like build on it to do like this type of reductions, which is not necessarily like low curving something. So in range for this, you need to have like some sort of noise of
Nice to keep 13 slides.
Ah, yes. That was somewhat intense. Yes. I actually removed one. Ah.
Yeah, that's downstairs.
Comment on this one.